Welcome to Chapter 4 of Class 9 Science, Structure of the Atom. In this fascinating chapter, we'll journey deep inside the atom to discover its internal structure. Remember from Chapter 3 that Dalton thought atoms were indivisible, but we're about to discover that atoms have even smaller particles inside them. We'll explore how scientists like Thomson, Rutherford, and Bohr gradually uncovered the secrets of atomic structure through brilliant experiments and creative thinking. Get ready to shrink down to the atomic scale and explore the amazing world inside every atom. Let's begin with the discovery of subatomic particles. The first clues came from simple experiments with static electricity. When you comb your dry hair and it attracts small pieces of paper, or when you rub a glass rod with silk and it can move a balloon, you're actually seeing evidence of charged particles in matter. J.J. Thomson discovered the electron in 1897 using cathode ray tubes, finding they were negatively charged and incredibly light, about 2,000 times lighter than a hydrogen atom. Then E. Goldstein discovered positive rays, which led to the discovery of protons, positively charged particles much heavier than electrons. These discoveries proved that atoms were not indivisible as Dalton thought, but had internal structure. Now let's explore J.J. Thomson's atomic model, often called the Plum pudding model. After discovering electrons, Thomson needed to explain how atoms could be electrically neutral overall while containing negative electrons. He proposed that atoms were spheres of positive charge with electrons embedded throughout, like raisins in a pudding or seeds in a watermelon. Think of a blueberry muffin. The muffin itself represents the positive charge, and the blueberries represent the electrons scattered throughout. This model explained electrical neutrality but couldn't explain later experimental results. Thomson won the Nobel Prize in 1906 for his discovery of electrons and his work on atomic structure. Now we come to one of the most famous experiments in science history, Rutherford's gold foil experiment. Ernest Rutherford wanted to test Thomson's model by firing alpha particles at a very thin gold foil. Alpha particles are positively charged helium nuclei. Rutherford expected them to pass straight through with minor deflections. But the results were shocking. Most particles passed straight through, some were slightly deflected, and a few bounced straight back. Rutherford said it was as incredible as if you fired a cannonball at tissue paper and it came back and hit you. This meant atoms were mostly empty space with a small, dense, positively charged nucleus at the center. Rutherford's nuclear model revolutionized our understanding of atomic structure. Rutherford's model had a major problem though. According to classical physics, electrons orbiting the nucleus should continuously lose energy and spiral into the nucleus, making atoms unstable. But we know atoms are stable. Niels Bohr solved this problem with his quantum model. Bohr proposed that electrons can only orbit in specific allowed paths called stationary orbits or energy levels. In these orbits, electrons don't radiate energy. Energy is only emitted or absorbed when electrons jump between orbits. Bohr labeled these orbits K, L, M, N or N equals 1, 2, 3, 4. This model successfully explained atomic stability and why elements emit light at specific wavelengths. Bohr won the Nobel Prize in 1922 for this work. Now let's understand how electrons are distributed in these energy levels using the Bohr-Berry rules. The maximum number of electrons in a shell is given by the formula 2n², where n is the shell number. So the K shell n equals 1 can hold 2 electrons, the L shell n equals 2 can hold 8 electrons, the M shell n equals 3 can hold 18 electrons, and so on. However, the outermost shell can never have more than 8 electrons. Electrons fill the shells in order from lowest to highest energy. For example, sodium with atomic number 11 has electron distribution 2, 8, 1 meaning 2 electrons in K shell, 8 in L shell, and 1 in M shell. This arrangement determines an element's chemical properties. Let's explore valency, the combining capacity of atoms. Valency is determined by the number of electrons in the outermost shell, called valence electrons. Atoms react to achieve stable electron configurations, usually with 8 electrons in the outer shell, the octet rule. Metals tend to lose electrons to form positive ions, so their valency equals their valence electrons. For example, sodium with 1 valence electron has valency 1. Non-metals tend to gain electrons to form negative ions, so their valency equals 8 minus their valence electrons. For example, oxygen with 6 valence electrons has valency 2. Understanding valency helps us predict how elements will combine to form compounds. Now let's learn about atomic number and mass number. The atomic number, Z, is the number of protons in an atom's nucleus, and it defines the element. All carbon atoms have 6 protons, all oxygen atoms have 8 protons. The mass number, A, is the total number of protons and neutrons. Protons and neutrons are collectively called nucleons. We write atomic notation with the mass number on top and atomic number on bottom, like carbon-12 written as C prefix 12 and suffix 6. This tells us everything about the atom, element symbol, number of protons, number of neutrons, and mass. These numbers are fundamental to understanding atomic structure and the organization of the periodic table. Finally, let's explore isotopes and isobars. Isotopes are atoms of the same element that have the same atomic number but different mass numbers. They have the same number of protons but different numbers of neutrons. For example, carbon-12 has 6 protons and 6 neutrons, while carbon-14 has 6 protons and 8 neutrons. Isotopes have the same chemical properties but different physical properties. Isobars are atoms of different elements that have the same mass number but different atomic numbers. For example, argon-40 and calcium-40 both have mass number 40 but different numbers of protons. Most elements occur as mixtures of isotopes, which is why atomic masses in the periodic table are often not whole numbers, they're weighted averages of all naturally occurring isotopes.